Greetings and salutations, magical chemists. Today we're going to talk about enthalpy, or enthalpy change, which is delta H. It's known as the amount of energy that's absorbed or released as heat by a system per mole of reaction. Enthalpy is only measured in systems where the pressure is held constant, and it's usually measured in units of joules per mole reaction. When that's used as a conversion factor in dimensional analysis, it's written with a number of joules on top per 1 mole of reaction on the bottom. And so, if you've been using Q, or MCAT, to calculate the amount of energy absorbed or released, if you simply take Q and divide it by the moles of reaction, you have a very short and sweet formula for delta H. Now, this equation is not on your formula chart, but you don't really need it as long as you know the units. The units are joules per mole reaction, so that's Q divided by moles of reaction. Now, there are two different types of reactions we're going to study. There are reactions that absorb energy from the environment, and there are reactions that release energy to the environment. And those are endothermic and exothermic reactions. So when you see the prefix endo, you can think of energy in, or energy enters. And so you can show this on a potential energy diagram. Notice that the potential energy of your reactants is lower than the potential energy of the products because of the energy absorbed. You can even measure this energy absorbed from your potential energy diagram to calculate your delta H. So in an endothermic reaction, you will have a positive value for delta H. An exothermic reaction, of course, is the opposite. In this case, energy is released, or it exits. And so in a potential energy diagram of an exothermic reaction, you'll notice that the reactants have more potential energy than the products. And the difference between them is our negative delta H. It is important to recognize that the magnitude of the enthalpy change is directly proportional to the moles of reactants and products involved in the change. This should make sense. Burning something is an exothermic reaction. If you burn a little bit of something, you'll release a little heat. If you burn a lot of something, you'll release a lot of heat. There's one more piece of information given on this graph. It's called the activation energy. Now, this is the minimum amount of energy the reactants need to be able to proceed for the reaction to occur. This is not related to thermochemistry. This is actually related to kinetics. So we're going to study activation energy, or the height of this bump, a lot next unit. Okay. Now, let's talk about thermochemical equations. Hopefully you remember a thermochemical equation from pre-AP. This is just when you include the energy change, or your enthalpy, within the balanced chemical equation. So let's take a look at how thermochemical equations work. Okay, first, just a quick reminder of the difference between endo and exothermic. Now remember, endothermic reaction, this is the one where energy is entering. So these actually feel cold to the touch because energy is being absorbed by the system, so the surroundings are losing heat. It's important to recognize that the heat energy being absorbed from the surroundings is being changed to potential energy in the system. The temperature of the system of your endothermic reaction or phase change is not necessarily going to increase. It could, but it doesn't have to. Now, of course, because you are gaining energy from the system, you have a positive Q when you calculate an MCAT, which means you have a positive delta H. So this is what happens whenever you are breaking or ending chemical bonds. Well, it's always going to be endothermic. And this doesn't even have to be chemical bonds. This could be merely attractions, intermolecular forces, or the attraction between a nucleus and an electron. So it takes energy to break a chemical bond or attraction. And so in this case, the energy required to break the reactant bonds is going to be greater than the energy released by forming product bonds. And so in an endothermic process, because energy is being added to the system, energy appears as a reactant in the balanced chemical equation when you're writing a thermochemical equation. So let's take a look. So here is a delicious example of when you are dissolving ammonia in water, and it forms the ammonium ion plus hydroxide, steals a proton basically. Notice, because we're telling you, delta H is positive. This is an endothermic example. So what that means is because it's positive, we're going to add it to the reactant side. So we take the value of 92. Now notice how it's 92 kilojoules per mole of reaction. When you write it within the reaction, we write it just as 92 kilojoules. Because when it's within the chemical reaction, that's implied. When this runs 1 mole of times, it will take 92 kilojoules. So notice the difference in units. Delta H by itself is kilojoules per mole reaction. But within an equation, we just say kilojoules because the moles of reaction are implied. Now let's look at exothermic reactions. Now, exothermic, of course, is when energy exits. It's released by the system. Exothermic systems will feel warm to the touch because the surroundings are gaining the heat that's being released by the system. Of course, the energy change is coming from potential energy of the system. That means the temperature of the system is not necessarily decreasing even when an exothermic process is occurring. Now, since it's exothermic, our calculated change in energy is negative, so delta H, of course, is negative. So it is always going to be an exothermic process when you're forming new chemical bonds or new attractions. And in an exothermic chemical change, the energy required to break the reactant bonds is less than the energy released by forming the products. And so, of course, because energy is being produced, energy appears on the product side of your thermochemical equation. Well, let's look at an example exothermic process. So in this case, it's the synthesis of ammonia. So this is exothermic. We know this because they told us, look, delta H is negative 324 kilojoules per mole reaction. So since it's negative, you're going to add it to the products, but be careful. Make sure you add it as a positive value. The fact that it shows up as the products is the indicator that it's being released. You don't need a negative sign. And in fact, if you add a negative sign, you would be wrong. So we add a positive 324 kilojoules to the product side. Remember, per mole of reaction is implied, so it's just kilojoules when written in the form of a thermochemical equation. Okay, so now that's when we're talking a lot about chemical changes, but you can also talk about endo or exothermic phase changes or changes within states of matter. So let's go ahead and look at the differences between like if you're changing from a solid to a liquid or a liquid to a gas. Well, first things first, remember that as you're going up from solid to a liquid, liquid to a gas, you are increasing in energy. So this means any time that you are going from a solid to a liquid, or a liquid is vaporizing to a gas, or a solid is subliming directly to a gas, in all of those cases you're going from a lower energy state of matter to a higher energy state, so you must be adding energy to the system. So all of these changes are endothermic phase changes. Conversely, if a gas is condensing to a liquid is freezing into a solid, or a gas is depositing directly into a solid, all of these are going to be exothermic changes. I realize it just failed at my color scheme. Oh no! It's weird to think about because it's like, why would the ones be orange when you're going down to a lower energy state? But remember, if the system is releasing energy, these are the things that actually feel warm to the touch. You're probably thinking, wait, ice does not feel warm to the touch. Well, that's because ice, if you're in ice, usually everything around it is cold. You're either in the freezer or maybe occasionally you're outside. All right, so now that we've got that, let's try a couple of practice problems. So notice I am giving you a couple of different examples. In some of these examples, I'm giving you a delta H within the equation, and in some of them, I'm giving you a separate delta H. Your job is, if it's within the equation, well, you need to write it separately. And if it's separately, you need to write it in the form of a thermochemical equation. So if this makes sense, if you remember this from pre-AP, you're like, I'm good to go ahead and pause the video and try it. If you would like me to do an example with you, well, I'll go ahead and do the very first one with you. But if you feel like you got it, then don't wait for me. Okay, first, this one's short and sweet because your energy is a product. So hopefully you can recognize automatically that this is an exothermic process because energy is being released. It's being produced, technically. Now, when we want to write an equation with a separate delta H, of course you probably notice I made stuff up that's not potassium, they're just random letters. So we have K plus M producing N. And now we need to write our delta H separately. So the enthalpy of our reaction, which we would put a little RxN to show it's of the entire reaction, well, notice in this case, the energy is being produced, aka released. So you have to realize this is going to be a negative 45. And then remember our units. We're not within the equation anymore, so it's not just kilojoules. It's kilojoules per mole reaction. Not too bad. All right, so go ahead and try these next two if you haven't already. And when you are ready to check your answer, unpause the video. Okay, how did you do? Now remember, the sneaky one to watch out for, notice on this last example, that is a positive 35 kilojoules being produced at the end. Make sure you got those units. It's just kilojoules when written in the form of a thermochemical equation. Other than that, I'm hoping this is short and sweet. All right, let's try a couple more example problems. Graphs. Everyone loves graphs, especially potential energy diagrams. So take a moment to answer questions 1, 2, 3, and 4. And when you are ready to check the answers, well, you should unpause the video. Hopefully on this first one, you can tell clearly this is an endothermic process. It's got a positive delta H because the products have a higher potential energy than the reactants do. Well, to figure out the difference in energy, all you have to do is subtract. So notice it ended at 300 kilojoules, but it started at 250. Well, 300 minus 250, that is just 50 kilojoules, which means it's positive 50 kilojoules per mole reaction. Okay, so for the next one, this one clearly then is exothermic. Because in this case, your products have less potential energy than the reactants. How much less? Well, let's subtract. We started out with 350 kilojoules, we ended up with 350, final minus initial, but we started with 450. So in this case, your enthalpy change was a negative 100 kilojoules per mole reaction. So short and sweet, we are just reading the graph. All right, we've just got a couple more practice problems and then you shall be free. Whee! All right, so looking at these different processes, we're going to identify, are they endothermic or exothermic, and why? If you're feeling brave, pause the video and try them yourself. If you're feeling a little less brave, I will go ahead and try an example with you. So for the very first one, notice we've got a single hydrogen atom plus another hydrogen atom, and they are, forming a chemical bond. Well, I hope you remember that forming new chemical bonds, you're always going to a more stable place, so these are exothermic because the energy is being released. And as for reason, you can literally say it's forming a new bond. Now for the second example, you'll be like, wait a second, why are they throwing electrons in there? This isn't redox. You can throw electrons anywhere. Notice you have an electron and you have a neutral fluorine atom which desperately wants that electron, and it grabs it. Well, you're not exactly forming a bond, but you are definitely forming an attraction, right? The electron is very attracted to that nucleus. So this is still an exothermic process. Okay, if you have not done so already, try the last two. And when you are ready to check your answer, unpause the video. So how'd you do? Okay, hopefully you realized that if forming the attraction between fluorine and the electron is exothermic, then breaking it must be endothermic. You are ending an attraction, so it is an endothermic process. Now, when you're going from a gas to a liquid, you are going to a lower energy phase, or lower energy state of matter. But you could also think about this if you remember your intermolecular forces. Yum! You are forming intermolecular forces as you go from a gas to a liquid. Well, that's an attraction, so forming new attractions is always going to be exothermic. Ta-da! You are done with this video. How very exciting. Now you're ready to move forward, onward, and upward into energy stoichiometry. Oh wait, did I laugh evilly? I didn't mean to do that.